Welcome to the flock. Let's dive into some practice with precipitates and applying the solubility rules. If you are given the following chemical equation, silver nitrate plus copper forms what? Automatically you should recognize that this is a single replacement reaction, where copper will replace the cation silver and pair with the polyatomic ion nitrate instead, in its place. What we would then have is copper and nitrate together plus silver alone. We're not going to concern ourselves with the charge of copper here. We know that nitrate always has -1 charge, and silver is a number 1 stunner. However, it's not important for us to know the charges here to determine whether or not there's a precipitate. We want to know if there is a precipitate, i.e. a solid, insoluble product that formed from this chemical reaction. We need to compare our product side, that's the copper nitrate and silver side of the chemical reaction, to our solubility rules. This chemical reaction is also known as a redox reaction, where one of the chemicals gets reduced and the other gets oxidized, which is basically just a fancy way of saying that one of them gains electrons and another loses electrons. And those movement of electrons are also how electricity functions. That's the premise of all redox reactions. So if we were to stick solid copper into a solution of silver nitrate, what would happen? We know that copper nitrate is one of the compounds that forms. Nitrate happens to be in the always soluble list. Therefore, copper nitrate would remain in solution, AQ. However, silver is by itself, and anytime we have an element by itself, it typically ends up being the solid. So this is more of an intuitive reminder from the state symbols list that we have aqueous, gas, pure liquid, and solids as options for our chemicals. And solids occur when you have insoluble compounds or an exception to the soluble rules, or if an element happens to be alone by itself, like silver in this case. So that would be our solid. So if we were to mix silver nitrate and solid copper in a beaker together and let it sit, you would see silver plating out onto the copper wire or copper plate, whatever it is you placed in the silver nitrate. As a reminder, there are other ways to show the solubility rules, both in table format or in a column row format, where you can pick out the cation and the anion to pair together to see if they are soluble, slightly soluble, or insoluble altogether. Soluble meaning that it does dissolve in solution, it is AQ for aqueous. Insoluble meaning that it does not dissolve in solution, it is S for solid, or precipitate. Now that we've tried a really hard one together, i.e. a single replacement redox reaction, go ahead and pause the video here to give this chemical reaction, a double replacement reaction, a try. See if there is a precipitate that forms in the products. Ready? Go! This is a double replacement reaction, as we stated before, so we know that the cation of one compound will pair with the anion of the other. We would end up with the products of sodium nitrate and barium carbonate. In this case, our charge is balanced, so we don't have to drop and swap. Now we need to apply the solubility rules to our product side of our equation. We have sodium nitrate. Well, gee, sodium and nitrate happen to be in the always soluble list. Therefore, we could say that sodium nitrate is an aqueous product. It's in solution. Remember that when we have a double replacement reaction, we're assuming that the reactants are also in solution. What about the barium carbonate? Let's see if we can find either barium or carbonate anywhere in our solubility rules list. I see barium here, and I see carbonate here. We see that the barium would be insoluble if it were paired with sulfate. Remember, sulfate is soluble unless it is paired with barium. Then that would make it insoluble. In this case, it's not paired with sulfate, so that doesn't help us much. How about the carbonate aspect? We look down at carbonate and we see that that would be insoluble unless it happened to be paired with an always soluble. Since barium is not one of the items on our always soluble list, we know that carbonate itself is an insoluble compound. Therefore, we can say that barium carbonate would be our solid precipitate product. All right, think you've got the idea of applying these solubility rules? Give these 3 double replacement reactions a try and see if you can figure out if there is a precipitate in the products. Ready? Go! Ready to check your answers? Let's do this. Since the hydroxide is an insoluble compound and it's not paired with any of the exceptions in our list, we know that aluminum hydroxide must be our solid precipitate product for the first question. Notice for the second one, we didn't have a precipitate drop out of solution. There doesn't always have to be a precipitate. As we can see, the sulfate here is a soluble compound, and it's currently not paired with any of the exceptions, therefore we know that H2SO4, sulfuric acid, would be soluble, or aqueous. This one was a trick compound for you. Notice that there's no copper anywhere on our list, not even in any of the tables that I've provided either, nor is there a cyanide, CN, polyatomic ion, anywhere to be found for us to determine whether or not this compound would be soluble or insoluble. This is where we need to resort to our MSDS. So let's do a quick search online for copper 2 cyanide solubility. We can see as the first hit that it is insoluble in water. Based on the first hit in Google, we can see that it is insoluble in H2O, but it is soluble in acid and alkaline solutions. So it's important to keep in mind that these solubility rules are just a generalization for us to be able to make quick discernments about whether or not a precipitate will be there. Sometimes we're going to have to look up online or in an MSDS sheet to figure out the solubility of a certain particular compound that's not included in our solubility rules list. And the only way we've known what's soluble or insoluble is through experimentation. Hopefully you understand this concept well enough now to ace this challenge question. Go ahead and pause the video here and give it a try. Let's check your answer and see if you got it right. Well, how on earth did I figure that out? I know that there still has to be a cation and an anion paired together. So the only option for decomposition or breaking apart of this chemical formula is to have something that could be by itself, i.e. oxygen, a diatomic, and to still keep a cation paired with an anion. Now let's look at the other compound. First and foremost, we know that oxygen, O2, is a gas, because that's what we kind of need to breathe in to live. We also have potassium chloride. Potassium, K, is in our always soluble list, and chlorine is also a soluble compound. Therefore, we know that KCl would be an aqueous product if it were in solution. It is capable of dissolving in water. So is there a water-soluble product formed? Absolutely. KCl would 100% dissolve in water. Let's see if you can test yourself before you wreck yourself. Go ahead and try and fill out this experimental table between reactant 1 on the top and reactant 2 on the sides to figure out the products that would form in double replacement reaction. Then try to determine if one of those products would be a precipitate. For example, if we were to take barium nitrate and react it with sodium sulfate, would that create a solid precipitate as one of the products? I mixed drops of each one of these chemicals together for you to see what it would look like experimentally. You can kind of check your answers to see if there is a precipitate or not based off of which of these little dot bubbles have a color in them. That color represents a precipitate, a solid that dropped out of solution. So you'll know which one of these should have a solid product in them. If you're stuck on applying these solubility rules, please comment below and I'll be happy to help out in any way that I can. Today we reviewed the solubility rules and applied them to various different types of chemical reactions, including a single replacement redox reaction, double replacement reactions, where we'll most likely be applying the solubility rules in the first place, and we even touched base on a decomposition reaction to determine whether or not a product would be water soluble. Please give this video a cool wax up, and I hope your day is just ducky.
No ducks, no glory.